Howdy, so you're here watching this video maybe because we're getting to a level of complexity with our Lewis structures. Maybe you need a little extra teaching. So here's a tutorial. What we're going to do in this particular tutorial is we're going to start with our basic Lewis structures. Some that, pretty simple. We don't have to worry about drawing them more than one way or finding formal charges, but we'll work our way up to more and more layers of complexity and more decisions that have to be made in terms of trying to pick the right one. So these first two, carbon tetrabromide and ammonia, those will both be taken care of in that first set of rules we learned way back on Chem Quest 1. So I do want you guys to have this sheet in front of you. I'll tell you what, I think on the test I'm actually going to allow you to use this. Me being the generous, kind person that I am, I'll let you guys use this on the test because it doesn't really tell you how best to make decisions. I guess it gives you rules, but you need to be able to apply those rules. That's what I want to see if you can do, okay? So you probably get to use this on your test, all right? So go ahead and have this in front of you, and of course you're gonna want your periodic table, all right? That's that always tool that we're gonna want, all right? And so we're going to walk through the first two basic ones where I don't have to do any of these extra steps, 6, 7, and 8 from that sheet. I don't have to worry about resonance structures. I don't have to worry about using formal charges and electronegativity to decide which one's best. All right? So let's get to work here. So I've got carbon tetrabromide. So step 1 from the sheet says to determine the total number of valence electrons that need to show up in my Lewis structure. All right? So what I do is I use the rule, right? Carbon is in the column that has 4 valence electrons. So I've got 1 carbon, so I'm gonna go 4 plus 4 times, so that tells me I have 4 bromines. So each bromine is in the column with 7 valence electrons. So this is gonna be 28 plus 4 equals 32. So that tells me when I draw this Lewis structure, I need 32 valence electrons to show up in my drawing. Okay? Now, the next step is to determine which, if any, is going to serve as the central atom. And one of those rules, by the way, is we never pick hydrogen. Hydrogen is always terminal, never going to be a central atom. Okay? And there's multiple ways to make a good guess as to what your central atom is, but typically it's going to be the one with no subscript or fewer subscript, or the one that has a lower electronegativity. All right? So between carbon and bromine, carbon does have a lower electronegativity and it has fewer subscripts, so that makes carbon the easy choice for our central atom. All right, so I'm gonna put C, and then I'm gonna draw my skeleton. So I have 4 bromines, so I'm just gonna draw a bromine on each side of carbon. Okay, so that is what we call a skeleton structure. So that's my basic structure. Okay, the next thing I'm going to do then is I'm going to look at my total number of valence electrons, which is 32, and I'm going to try to put all 32 electrons in. And I'm going to always start by putting electrons on the outer elements first. The only exception there is I never put extra dots on hydrogen, right? None of these are hydrogen, so they can all get some extra dots. Okay, and we're going to follow our octet rule. So each line counts as 2 electrons, 2 valence electrons total. So of these 32, I've already shown 8 by just drawing my skeletons. There's 2, 4, 6, and 8. Okay, so next step is I'm going to go around my bromines and add dots. All right, until I run out of space. Darn L every time. All right. Anyway, so. It doesn't matter which bromine I start with. I'm going to put 2 there, 2 there, 2 there. So there's my 2, 4, 6, 8 on that bromine. 2 there, 2 there, 2 there, 10, 12, 14, 16, and an octet. 2, 4, 6, 8. There makes 24 with an octet on that bromine. And 1, 2, 3, 4, 6, 7, 8. There makes 32 with an octet around each bromine. All right? So I've got all 32 electrons that need to be assigned. All right? So I can maybe put a little check there to say that I'm satisfied with that step. Now, what that means, and a common mistake is sometimes you guys want to start throwing electrons on your central atom when you don't need to. You only put dots on the central atom if there's nowhere else to put them. So that might mean there's hydrogens around the outside, or it might mean that you have some extra electrons after you filled your atoms. That happens. Okay, but in this case, I've got all 32 in there. I don't need any dots on my central atom. So the next thing I do then is I check my central atom to make sure it also has an octet at this point, right? So I've got an octet around each of my bromines. That did that by filling up with my 32 electrons. All right, now I'm going to go to carbon here, and I've got 2, 4, 6, 8. Remembering each line counts as 2. Also an octet around carbon. So at that point, I've got all my rules met. I've got all 32 electrons in there. I've got an octet around each of the elements that needs an octet. There's no other way to draw that. So, done. Just like that. I don't need to worry about figuring out formal charges to figure out which one's best. Not with this one. That's good the way it is. All right? So let's go to ammonia now. Okay, we're going to do this one similarly. With ammonia, nitrogen has 5 valence electrons, and I got 3 hydrogens at 1 valence electron each. That gives me 8. All right. Now, you guys heard me in class say that whenever this is a multiple of 8, you don't put dots on the central atom, right? Hydrogen is our oddball. Can't put any dots on hydrogen. All right. So, slight caveat to that rule. So I'm going to make my skeleton N, H, H, and H, right? So there's my skeleton. Of those 8 electrons, I've got 2, 4, 6. Now, normally, I would take whatever leftover electrons I have and put them on the outer elements, but all those are hydrogens, and I don't put dots on hydrogens, right? So the only other place I can put them is on the central atom. And again, I don't put dots on the central atom unless I need to, unless there's nowhere else to put them. All right, I cannot put those extra 2 electrons on the hydrogens, so you kind of have to go in my central atom. Boop. All right, so now I'm showing 2, 4, 6, 8 electrons. Those 8 are taken care of. Okay, now I'm going to check for my octet. Now, hydrogen doesn't get an octet; it gets 1 line. That's it. That's all it needs. Okay, so my 3 hydrogens have their 1 bond. They've got their duet, I guess you might call it, to make it like helium. Nitrogen, on the other hand, does need an octet. So let's check 2, 4, 6, 8 on the nitrogen. I've got that octet met. No other way to draw this. I can't make any double bonds with hydrogen. No need for that. Good to go. Octet around nitrogen. 1, 2, 3. Got all 8 electrons. Done. So again, oftentimes, these first little set of 5 rules right there take care of things for us, okay? All right, so let's add a little bit of complexity to this, all right? Let's move on to a nitrate polyatomic ion. All right, and what nitrate will allow us to do is talk about both formal charges and resonance structures at the same time, so we can kind of kill 2 birds with 1 stone. So nitrate is a polyatomic ion, which means, yes, it is an ion, but these 2 guys, the nitrogen and oxygen, are covalently bonded, and then they eventually get an extra electron from somewhere, probably a metal, okay? And so that little minus charge tells me this is a polyatomic anion, or negatively charged ion, but it's formed from a covalent molecule, okay? So this anion by itself is going to take on a particular structure, okay, that has overall charge of -1. We'll kind of show you where that comes from in this little part of the lecture too, okay? So, same rules. We're still going to start here, just like we always have, but in this case, we're going to have to go a little farther down to make sure we're doing things correctly. All right, so we're going to start with nitrogen, which has 5 valence electrons, plus I've got 3 oxygens, 3 times 6. Each oxygen has 6 valence electrons. Now, I need to account for that little minus charge right there. It's a -1, which tells me I have 1 extra electron as part of that molecule. Okay? If it was a -2, I would put +2. If this was a plus, like for ammonia, I would actually subtract 1. So for example, NH4 plus would be 5 plus 4 times 1 minus 1, because that positive means I got rid of an electron. All right? That being said, let's go back to our nitrate here. So 5 plus 18 plus 1 gives me, so this 18 plus 5 is 23 plus 1, 24 valence electrons. All right? Now, between nitrogen and oxygen, nitrogen has a lower electronegativity, so that's going to be my central atom. I'm going to go N, O, O, O. Now, so how many electrons am I showing so far? 2, 4, 6. I need to put in 24 of them. All right? So I'll go to my outer elements first. I'm not going to put any dots on nitrogen unless I have to, unless there's nowhere else to put them. Remember that. All right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Do I need to put any dots on nitrogen? Nope. I don't have enough electrons to do so. All right? So, the next step then here is check for octets. All my oxygens have their octet. That's good. What I don't have is an octet around my nitrogen. All right? So, when I don't have an octet on my central atom, I need to then make another bond with one of the outer elements. Okay? Now, these being oxygen, all 3 of them being oxygen, it doesn't matter which oxygen I choose at this point. All right? So I'll just pick this one. All right? Now, to make my double bond, right, I'm going to take one lone pair, erase it from existence, and turn it into a bond. So, in fact, the nitrate polyatomic ion has one double bond to one of the oxygens, and then 2 single bonds. Okay? That's what that looks like. Now, at this point, you might be wondering, well, what happens if I decide to make a double bond here or here? It is the same thing. Sometimes I'm going to say, okay, now I want you to draw all possible Lewis structures. Okay, in which case you would draw this again, but we'll just move our double bond. So we could draw it like this, or we could draw the double bond here. Or we could draw a double bond here. Okay, and what I want you to recognize here is these are all equally likely. Okay, they're equally likely because all 3 show one double bond with an oxygen, one of the 3. And each oxygen is just as likely to have a double bond as the others. In reality, what's probably going to happen is that double bond is going to rotate through those oxygens. They're going to take turns having that double bond. Okay? So those are called resonance structures. And in this case, we would draw all 3 of them because there's an equal likelihood of that double bond being in any one of those 3 locations. Okay? So when I say draw all possible resonance structures, this is what I mean. All right? Now, formal charges. We're going to talk about how to use formal charges to identify sometimes if one is better than the other. All right. But next thing I want to add in here, though, is I do want to introduce formal charges and kind of where that little negative comes from. All right. Again, remember it comes from an extra electron, but let's look at where these charges are. All right. Now, the formal charges will not make a difference in how I draw these 3 because they're all the same thing essentially, just movement. But this is a good chance to talk about formal charges. So, formal charges is valence electrons minus formal electrons. If you guys got that from class, all right. If you missed that day in class, make sure you write that down. Formal electrons, valence minus formal, or formal charge, excuse me. All right. So, oxygen has 6 valence electrons, right? So for this one, I'm going to go 6 minus the number of formal electrons. electrons. Now, I've got 1, 2, 3, 4 right there. And then what we have to picture are bonds as one formal electron per atom in the bond. So in this case, I've got 1, 2, 3, 4, 5, 6. So those lines right there for formal electrons don't count as 2. They count as 1 each. Okay? So in this case, I've got 6 minus 6 equals 0. All right? On this oxygen, though, again, there's 1 there and 1 there. So we're going to differentiate those. I've got 1, 2, 3, 4, 5, 6, 7. So that's 6 minus 7 equals negative 1. This oxygen is just like that one. So 1 there. 6 minus 7 equals negative 1. And then on the nitrogen, has 5 valence electrons minus 1, 2, 3, 4 equals plus 1. All right? So of my formal charges, I've got negative 1 there, negative 1 there, and a plus 1 there. All right? It's actually a lot of formal charges, but any way I dice this guy up, I'm going to get the same number of formal charges. It looks the same on this one and this one. Okay, so again, valence electrons, we know how to do that. Formal electrons, when you look at a bond line counts as 1 electron for the oxygen and 1 for the nitrogen. And each dot, of course, counts as 1. So I've got 1, 2, 3, 4, 5, 6 that actually count for that oxygen. So that's the 6 valence electrons from the periodic table minus 6 formal electrons gives me a formal charge of 0 on that oxygen. There's 7 formal electrons here. 1, 2, 3, 4, 5, 6, 7. 6 minus 7, negative 1. Same thing there. And then 5 valence electrons for nitrogen minus 4 formal. 1, 2, 3, 4 gives me a plus 1. Okay? Now you'll notice that the overall charge of my nitrate is a minus 1. All right? If I go minus 1 plus minus 1 plus 1, that gives me a minus 1 overall charge that matches that polyatomic ion. All right? Now, you need to be able to assign formal charges when asked to do so. But what you also need to be able to do is determine whether one structure is better than another one based on formal charges. Now, because these all end up exactly the same, there's no differentiation to make there. They're all equally likely, and that matches that, so that's a quick way to check. Okay? So what we'll do next is go on to how we can use formal charges in a molecule to determine whether one is better than others. I'm going to make this into 2 separate videos, so I'm going to stop this one. This one just takes us up through the first 5 steps, and then resonance structures, and then how to get formal charges. All right? Next video will take us through a couple more complex ones where we then have to use formal charges to determine if one is better than the other one. And then that last little piece down there with electronegativity, what if we use formal charges and we still can't differentiate as to which one's best? Can we use another property to figure out if one is more likely than others? Okay? But that's it for this video. Stay tuned for the next one to get more on formal charges and electronegativity and deciding which molecule or which structure is best for the molecule in question. All right?